Well, hello. My name is Chris Barkin. I want to welcome you to the William W. Hay Railroad Engineering Seminar. Before I introduce our speaker, I'd like to take care of a few housekeeping items. If you have a cell phone, please turn it off or put it on mute so it doesn't interrupt the speaker, including the speaker's cell phone. If we have a fire alarm, exit from these doors and go to the nearest safe stairway, across the lobby in that direction and right down the hall on the right on this direction. We'll carefully cross Main Street, which is the street behind you, and assemble next to the Hydro Systems lab. We'll use the buddy system, so please note who's next to you and watch out for each other as you reassemble. If we have severe weather, which we're not expecting today any other than the remnants of the hurricane, but if we did, we would, again, not go outside, but we would go out that door or that door and back over to the old portion of Newmark. As soon as we walk into the old section of Newmark, we'd go down the stairs all the way to the basement, which is a very safe sanctuary from any severe weather. If you did not swipe your ID card earlier, please be sure to sign the attendance sheet we're passing around, including your name and affiliation. And if you did not receive a direct email announcement of this seminar but would like to in the future, please legibly include your email address. Also, I'll say to the speaker, we'll try to get a microphone to people in the room if they have questions, but if not, please repeat their question for the benefit of the audience that's tuning in online. The William W. Hay Railroad Seminar Series is sponsored by the Rail Transportation and Engineering Center here at the University of Illinois at Urbana-Champaign. And on behalf of all of us, we thank AAR, BNSF, CN, Hanson Professional Services, and the National University Rail Center of Excellence for their ongoing support of Railtech. It's greatly appreciated by those of us here on campus as well as those participating via the internet. I'd also like to welcome the more than 140 people who have registered for this seminar. They hail from 10 different nations and 5 different continents. The list of attendees includes freight and passenger railroads, transit organizations, federal and state DOTs, engineering firms, universities, research organizations, and technology developers and suppliers and others. We're very pleased that you could join us today. Those of you who wish to receive PDHs for your participation, please see the instructions at the web page and in the information that you in the email you described announcing this seminar. So in the face of rapidly advancing technology to reduce the energy consumption and emissions of highway trucks, railroads need to maintain their position as the green transportation mode. They must continue to advance in both energy efficiency and emissions. The rail industry is thus presented with a dual challenge of both decarbonizing, that is eliminating the release of carbon, and improving efficiency to reduce the amount of energy expended per unit of transport. Our speaker today will discuss advancements and new insights since his previous Hay seminar addressing this dual challenge in June 2021. And that seminar was virtual, so we're very pleased to have Mike here in person this time. And he'll talk about what changes have occurred, how much progress has been made, and where does the industry stand regarding 2030 and 2050 targets. We're exceptionally lucky to have our speaker today, Mike Iden. He's a locomotive and railroad technology consultant with over 45 years of employment in the rail industry, where he worked for the Southern Railway, Chicago and Northwestern, and Union Pacific, and also with the Electromotive division of General Motors. Much of his railroad career was devoted to new locomotive designs and technologies, and projects he managed include transitioning the CNNW into high adhesion and AC traction locomotives, expanding Locotrol, and then distributed power technology, and standardizing and modernizing UP's locomotive fleet with 2 major mergers. He was responsible for the earliest efforts regarding ultra-low emissions locomotives, including diesel battery hybrids and multi-engine switchers. His complete list of projects is far too numerous to list here, but suffice it to say that he's had extensive experience and has really been a thought leader in the subject that he's talking about today. He completed his BS degree in mechanical engineering at the Milwaukee School of Engineering and a Master of Management degree from Northwestern as an EMD fellow. Mr. Iden is a registered professional engineer in 3 states, and he served as a member of numerous AAR committees, including serving as the chair of several of them, among them the Locomotive Committee, which is where I first met Mike over probably almost 30 years ago.
Yeah, 30 years.
He remains quite active as a consultant, writer, and instructor in the rail industry, and among his current projects is one with our former colleague, Professor Tyler Dick at the University of Texas, conducting a cost-benefit and risk analysis of railroad electrification for the FRA. I'm very pleased to introduce Mr. Michael Iden, who will present his seminar entitled Freight Railroad Decarbonization and Energy Efficiency version 2.0.
Thank you, Dr. Barkin. Is anybody, I presume you're all familiar with the artwork at, what is it, Wright in Green Street's alma mater?
The statue, the alma mater.
The statue? Okay. And I'm going to slightly change the inscription. To the happy engineers of the future, those of the past send greetings. And I consider myself to be an engineer of the past because of my age. And I've been fortunate to have had a career that I can still enjoy, and a family that supports that endeavor when we're not babysitting grandkids, which is even better. But has anybody not used a slide rule in here? Be honest. Okay. When I took my EIT and PE exams in Milwaukee, was at the University of Wisconsin campus. I think there were 80 candidates in the room, and one had a calculator. This was late 1972. One had a calculator, and he did not bring an extension cord. So that was lesson number one before I graduated regarding technology. Again, as Dr. Barkin said, we're going to do a redo here, a relook at the Hay seminar that I presented June 4th of 2021. The dual challenge, decarbonization and increased energy efficiency. And flip out that last left-hand light switch. Oh, yeah, thank you. The presentations, obviously, I think most of you have them. Why are we not moving forward here? What happened? Yeah, I think we lost something here, Emma. Oh, sorry. The presentation is on the web, and there's also a YouTube. There it is, right there. Okay. Okay. So, anyway, there's those are the links. A very quick synopsis. What we're going to talk about. 8 modules here. We're not going to have time to go in depth, so it's going to be kind of a high level. And I want to preface this by making a pronouncement here that I have no favorite pick for technology in the future in terms of railroad propulsion. There's a variety out there. There are a lot of things going on. The state of California, the Air Resources Board, they've come out with a regulation which I think most of you probably know. The Association of American Railroads and I think the Short Line Association are both fighting in court, which in simple words would radically and I think dangerously force the adoption of technologies that ultimately may and probably should play some part in the railroad freight industry, but it's unfortunately a too rapid of a change. And I'm not going to get into that, but that is one of the things that is in the background here. And the other thing, I'm going to mention electrification, and I feel that when the word electrification comes up, pulse rates go up, and there's a view that whoever mentions electrification is speaking of, for example, Switzerland, where 99.9% of the tracks, including virtually every track and every rail yard, is electrified with 15,000 volt AC catenary. That's not the direction I'm going in. It may be the direction other people think about when they talk about electrification. That's not my view, and we'll talk a little further about that. Decarbonization, of course, you know the famous song by Joe Raposo, sung by Hermit the Frog, it ain't easy being green. And 2 things I want to point out here. Excuse me. July 29th, it was in the media, Air New Zealand has withdrawn its 2030 commitment with the Science-Based Target Initiative, SBTI, which is one of the two decarbonization goaltenders, I call them. And the reason Air New Zealand withdrew was they are not going to get the new technology planes that they think are necessary. They will most likely not get sufficient sustainable aviation fuel, which is the aviation equivalent of renewable diesel. And overall, the risks of trying to pursue these options put their goals for 2030 at risk, and they've temporarily withdrawn them. They say they're still going to meet their net zero goal for 2050, but the details have to be reworked. And the second thing, this report just came out from University of Cambridge, I think the engineering school. It's called from the Aviation Impact Accelerator, and it's an interesting report. They talk about, and it sounds like the railroad industry, one way for the airlines to save fuel is to slow their planes down. You know, speed is power, power is more energy. And but what I found personally quite shocking, they are talking about what they call a moonshot for the commercial aviation world, to use hydrogen stored on board as a cryogenic liquid as fuel for modified jet engines on commercial airliners. And the problem I have with that is liquefied hydrogen has basically about 27% of the energy of jet fuel. And so the question is, how are you going to sustain the operating range with that much of a reduction in onboard energy? Maybe I've overlooked something, but you might want to take a look at that report. Energy efficiency. I wrote an article in the September issue of Railway Age called "How Does It Pencil?" And it's a term from I picked it up, it's a term from the real estate industry, largely in the New York area. And when developers are looking at a housing or a commercial development, a big box farm, you know, big box buildings, et cetera, they basically do a pencil. They put the numbers on paper and they just do a rough calculation. Does this project make sense? Should I invest my or our money? Am I going to get returns? What are the risks, et cetera? So I basically adopted that. And what I want to mention here, just so we set a common stage, whenever you have multiple changes in energy, when you go from, for example, crude oil to diesel fuel, diesel, put it in the engine, produce mechanical energy, then produce electrical energy, and then change it back to mechanical and do work at the rails. And energy and work are interchangeable. Every time you go through these steps, you end up with a multiplicative efficiency number at the very end. So I got an example here of 5 energy conversions, each one 99% efficient, and we end up with 95% efficiency at the end. If I drop one of those factors down to 50%, my overall efficiency goes down to 48%. And basically the rule here is the lowest single factor governs your overall efficiency. And if we go back in the history of the railroad industry, with steam locomotives, the best steam locomotives in the late 1940s, early 1950s were basically 8 to 9% efficient. And the boilers, the latest boilers, were 75 to 80% efficient. The lowest efficiency came from the reciprocating cylinder, and then followed by the rod mechanism on the driving wheels. But again, they were 8 to 9% efficient. And General Motors came out with the first commercially successful diesel locomotive, which was 23% efficient, looking at the diesel engine, the alternator, or the generator, traction motors, etc. And the diesel locomotives were more expensive than steam locomotives, but the overall economic efficiencies were such that the railroads in the US basically scrapped half of their fleet. Half the fleet was worn out by the Depression and World War II, and the other half was relatively new, less than 10 years old. The Class I railroads basically scrapped that technology, got rid of the intense shops and staffs that were required to maintain steam locomotives, and transitioned over to a more expensive liquid fuel. But overall, there were great efficiencies to be gained. Excuse me. Yes.
You know, that's an interesting point. It's not just the 23%. As you know, it's not just the 23% energy efficiency that drove this transition. It's what you just touched on, which is all the infrastructure
Right.
that they could get rid of. And I think there's analogs in some of the conversations we're having today about alternative energy, which is why
Thank you for bringing up the I word, infrastructure. And I have been, as Dr. Barkin commented on, I've been consulting and advising, trying to find clients and advising them. And there are clients out there who are interested and they want to learn more about the railroads, and they come with proposals and so on. But you need the machine and you need the infrastructure. And if there is any industry in modern civilization that is infrastructure dependent, it is railroads, particularly freight as well as passenger. But thank you for that comment. This is there's a proposal. It's been in the trade magazines, probably even in the newspapers. It's an offshore proposal, and it's an organization that they're going to take a 1993 diesel electric locomotive. I think it's roughly a 3,000 horsepower. It has an older 8-cylinder low-speed diesel engine, which has pretty good efficiency. The overall efficiency of the locomotive is probably around 32%, and they're gonna rip out the diesel engine and the generator. They're gonna leave the traction motors, and they're going to turn it into a locomotive that they will take green hydrogen produced by electrolysis, which will require renewable electricity to make it, not by steam methane reforming, which is where you cook natural gas and steam over a catalyst. So they're going to produce renewable hydrogen. They're going to compress it with 24% efficiency loss. They will then burn the hydrogen in a series of combustion chambers to produce steam. The steam will turn 4 steam turbines, which in turn will turn 20 electrical generators. So apparently there's going to be a gear mechanism between each turbine and at least five generators, and put all the energy, the electrical energy, into the original 6 DC traction motors. And by my math, they end up with a 15% efficient locomotive. And they're probably starting out with a 32%. But it's a zero emissions locomotive, but it comes, by my math, at a tremendous cost of poor energy efficiency. You're using twice as much energy to go green. And going back to Kermit, it's really hard being green. Excuse me. Okay, measuring energy efficiency. I want to make a comment here about the 2 primary forms of ground transportation: heavy-duty trucks and rails. Trucks historically have measured their fuel efficiency and published it in terms of miles per gallon, which is a very crude measure. You don't know how many ton miles they're producing, et cetera. But the historical average for heavy-duty trucks up until 2015 was basically 5 miles per gallon. And it's for an 80,000, roughly maximum 80,000 pound truck, that's not bad. Since 2015, there have been 3 projects which are jointly funded by DOE, Department of Energy, and the truck and trailer manufacturers and all the accessory manufacturers, including tire manufacturers, rear view mirror companies that are now going to digital cameras instead of a mirror sticking out being an air grab, and so on. And they've essentially, the newest trucks are now double the fuel efficiency. They've gone from 5 miles per gallon to 10 miles per gallon since 2015. Railroads have done pretty well also, freight railroads. Historically, and we measure in terms of gallons per 1,000 gross ton miles. Over 64 years, and I'll reference, I did an ASME paper back in 2014, 2015, 16, something like that, and 2019. And I looked at railroad fuel efficiency from 1920 to 2015 in 5-year increments, and I converted all the crude oil, all the bituminous, semi-bituminous, anthracite, coal, et cetera, and turned it into diesel equivalent gallons based on a BTU basis. And the peak energy consumption was 1945, the end of World War II, the last year of the war. And we were basically using 8 times more equivalent energy to handle 1/2 or 1/3 of the freight we do today. So we've made some good performance, and it's averaged about 1% per year. Now, I asked the question here, first of all, has anybody not heard about SuperTruck? If you haven't, okay, you've not heard about SuperTruck. Okay, I'm going to give you a real quick dunk in the deep end of the pool here. It's a jointly funded R&D and commercialization of technologies to improve Class 8 heavy-duty truck energy efficiency. And it started out in 2015 with $284 million, half DOE federal funds, half contributed by the suppliers for aerodynamics. And the goal was a 50% improvement in their miles per gallon. By aerodynamics, I'm referring to the skirts on the bottom of the trailers to redirect air away from the rear tires, the top of cab shield to direct air over the trailer instead of into the blunt front wall, other reductions, streamline, etc. SuperTruck 2 followed, and it was high-efficiency engines, taking diesel truck engines from 40+% all the way up to 55% efficiency, a high-efficiency transmission, and other improvements. And that basically took the heavy-duty trucks, the new trucks, from 5 miles per gallon, new tractor trailers from 5 miles per gallon to 10 miles per gallon. And now DOE and most of the same suppliers are jointly funding SuperTruck 3. What's the goal of SuperTruck 3? It's to come up with an electric transmission for a Class 8 tractor, which will enable the truck to generate its onboard energy from either hydrogen fuel cell or batteries. So this is, and when you add up the 3 SuperTruck programs, it's just short, by my math, just short of $700 million. This was to me, a golden opportunity for the trucking industry. And again, it's half federal dollars and half manufacturers. And most of the improvements have now been commercialized and are available for those who go out and buy Class 8 tractors and Class 8 semi-trailers. This is I call it a super summary, and basically I've got the citation at the top there. Again, SuperTruck 1 was aerodynamics, SuperTruck 2 is high efficiency engines, transmissions, and SuperTruck 3 is getting the trucks ready for fuel cells and batteries. And I also, in the lower left, I did in September issue of Railwage, I wrote a short article about SuperTruck and the new efficiency fever. I'm not a country western fan. I'll admit, when I'm driving on the interstate coming down here, I have a certain tolerance for Willie's Roadhouse, Willie Nelson, and I like some of the country western. And I stumbled on an old country western called Freightliner Fever from, I think it was 1965. And he talks about, blowing a freight train off the tracks coming out of LA with a Freightliner that obviously was cruising slightly above the speed limit. But the thought occurred to me, this is a great segue to talk about SuperTruck versus the railroad. So you might want to also look up that article and look up Freightliner Fever while you're at it. It's kind of a catchy tune. All right, Class 1 railroad energy or fuel efficiency then, now, and tomorrow. Again, I mentioned that I did an ASME paper. It was published in 2019, and I looked in 5-year increments from 1920 to 2015. I had ICC spreadsheets, the old published spreadsheets from the AAR library, and converted coal, all the coal, crude oil, et cetera, into diesel gallons equivalent. And this bold red line, you can see the peak for energy usage. We used in 1945, the freight railroads used the equivalent of 27 billion gallons of diesel fuel equivalent. And today we burn just over 3. So we used 8 times more energy than we do now, and we handled, in terms of gross ton miles, we handled about 13 billion gross ton miles, and now we are up here at, let's see, wait a minute, gross, well, I lost the scale here, but we're about 3 times better in terms of the work we're doing. So we've made a tremendous improvement in fuel efficiency. However, it averages out to a 1% improvement per year in gallons per 1,000 gross ton miles. And that would be my blue line here. The top line is revenue ton miles. Gross ton miles, I think, is more realistic because you have to move the freight car and the lading. That's why, I favor gross ton miles. But if you take this blue line and you extend it out here, this is a chart from Wayne Kennedy in Omaha, who was the general director of fuel conservation when I was in mechanical department at the UP. And we've worked together since then on a number of projects as well. But that's the average line for the 6 Class 1s in terms of gallons per 1,000 gross ton miles. And through an estimate for 2024, and you can see basically it was about a 1% downward, which is an improvement trend, but the last several years it has flattened out and it's actually taken a turn up. It's gotten worse. And what Wayne has done here is he's plotted this line, which is the fuel efficiency improvement that would be needed to get to the published SBTI goals for decarbonization by 2030. And the bottom line here is that instead of a flat or 1% improvement right now, the 6 Class 1s, by Wayne Kennedy's math, the 6 Class 1s will have to kickstart and get a 6.8% improvement in order to get down here. And if you're depending solely on fuel efficiency improvement to get to your 2030 goals. So again, this is another example of how energy efficiency and projections and goals for decarbonization get tied together. All right, next slide. Alternative locomotive energy efficiencies. I call this the taste test. I love to go shopping in a store. I love going to a hardware store. I love to look at, all the neat things and, what could I do with this? Tempted to buy it sometimes. I resist that because they end up on a shelf or in a drawer, and then the wife says, what did you buy this for? But I was shopping one day and I saw this display of a popular brand of soda pop, and I said, someday I'm going to use this photo, and here it is. So we're going to take a bit of I call it a taste test. Has everybody heard about Sankey diagrams? Okay. Just to be clear, Matthew Sankey, he was an Irish engineer, and he produced what is recorded as the first true Sankey diagram, which shows energy in and work out of a system. And the bottom diagram is a 1898 steam engine, assuming that it was thermodynamically ideal. And on the top was a state-of-the-art 1898 steam engine. And again, you can see the comparison. The work out is the same, but the ideal engine has a much lower energy input than the actual engine. And the difference is inefficiencies, friction, heat loss, et cetera, that makes the engine less efficient than the ideal engine. And in fact, it was Dr. Tyler Dick, who was formerly he got his PhD here. He's now a professor at University of Texas, Austin, who turned me on. It's called Sankey-matic. It's a free package, and I'll show you some of the Sankey diagrams I put together. But there's another Sankey diagram, and this is produced every year by Lawrence Livermore National Lab from DOE, and it shows the total energy use, sources and use for the United States. And the last diagram that's out there is for 2022. We used in 2022 100.3 quadrillion, I think it's BTUs of energy. And the biggest of all the sources and the uses, which are these pink boxes and electricity generation, and then of course the useful applications go into energy services, and all of the inefficiencies go into rejected energy. And if you divide energy services, which is useful energy, by the total, 100.3, you end up with roughly 33%. So 1/3 of all the energy we as a society use, 1/3 of all the energy, solar, wind, nuclear, hydro, coal, petroleum, etc., 67% of it goes away. It's not destroyed, it's lost, as friction, heat, etc. And the two greatest basically sinks for energy are electricity generation. It's 36% efficient, largely due to the remaining thermal coal generators, and transportation, 21% on average. We, the railroad industry, fall into that bucket, but the real sinkhole in transportation is the gasoline-powered automobile, which is nominally 15% efficient. So, you know, that's where a lot of the drive comes from for EVs, where you have much lower energy losses, but you have the classic issue of, do I have enough range? And it's going to be the same thing with going from diesel locomotives to battery locomotives. Okay, I took a crack at diesel electric locomotive efficiency. I believe you all have access to the book from the late Walter Simpson, Diesel Electric Locomotives. Okay, and Walter, by the way, passed away, I think, about 18 months ago. I didn't realize it until after he had passed away, but he was not an engineer. He was the energy manager for State University of New York at Buffalo. And he sent me his draft, and I went through it, and I was quite impressed with it. And then he sent me a copy of it, and I took time to go through it, and it's a book I would have loved to have written. And not being an engineer, I think he laid out very succinctly what a diesel electric locomotive is, how it works, how it doesn't work, and the details such as efficiency. So what I've done here, I'm assuming a Tier 4 latest diesel engine, and I've heard people say, well, the Tier 4 really isn't 44. I've had an expert who was involved in, you know, the design of one of the engines. He says it's 44%. So I'm going to take 44%. Alternator, roughly 96%. That's a number that the locomotive builders, they treat that like the formula for Coca-Cola. You know, the original formula, which is in a vault somewhere in Atlanta, and you, I, and nobody else is ever going to see the original formula. So that number it's a ballpark number. And then you go, you know, you rectify the AC, put it into the DC link, into the inverters to create a synthetic AC wave. You got the AC traction motors, you got the bull and the pinion gear, finally down to work at the rail. So I'm saying a diesel electric locomotive, latest engine, AC traction, we're 40% efficient at the rails. If I convert that into a Sankey diagram, this is what it looks like. And again, for consistency here, what I'm doing is I'm showing 1 unit of work at the rails, and if you want to back up, you can see we have to start out with by my math, 2.52 units of energy going in to get 1 unit of energy out at the rails as work. And this is where, if you do a calculation using the lower heating value of 5,000 gallons of diesel fuel, by my estimate, it's the equivalent of 192 megawatt hours of energy. The largest battery electric locomotive that's been announced so far is 14 megawatt hours. And it's for a mining company, from a US company, and it's for a mining railroad in Western Australia, and it's 14.2 megawatt hours nameplate capacity, and the actual usable is between 85 and 90%. So you can see the utility of liquid fuel. We've got basically 192 megawatt hours of energy. If you shake it down with the efficiency factor, you actually have 72 megawatt hours that are usable. So that to me is a benchmark that I compare future locomotives, particularly battery electric, against in terms of, can I do the same work that I'm doing now? Now, I want to branch off here and talk a real brief about diesel engines, large bore diesel engines, which are in locomotives, and proton exchange membrane or PEM fuel cells. There's been a lot of talk that fuel cells, if you put fuel cells on a locomotive, they will be 60% efficient. From what I've been able to find, fuel cells can be 60% efficient, but their peak efficiency is at lower power settings. That's the blue line. At full power PEM fuel cells, by what I have found, they get down to around 40%, maybe 50%, when you're at the equivalent of notch 8 or full power. Whereas a diesel engine, the efficiency for the most part keeps going up until you get up to full power. So to me, this is an issue that I think needs to be looked at more closely in discussions about potential fuel cell locomotives. Now, I took a crack at a Sankey diagram for a fuel cell locomotive. And again, let's back up here and let's look at the diesel electric. 2.5 units of energy going in, 1 unit of energy coming out. When I look at the fuel cell locomotive, by my math, when I pencil it, I start out with just under 4 units of energy, and I get 1 unit of energy out. And the biggest efficiency losses are, I start out with renewable electricity from a renewable grid, which we don't yet have. I lose 29% of the inbound energy to process inefficiencies in the electrolyzer, waste heat, et cetera, et cetera. And then to compress it, I have to use another 24% of the energy. I got 76% efficiency to take the raw hydrogen gas and compress it. If I want to liquefy it, my energy use is even greater than compressing it, so I'm just going to use 76% efficiency. The fuel cell itself, again, going back to what we showed here, I'm assuming 50%, somewhere in the middle between 60 and 50%. And again, the same 3 final transmission inverters, motors, and gears. I end up with, by my math, 25% of the inbound energy at the rails as useful work. And there's our Sankey diagram again. So by my math, I lose a total of 75% of the inbound renewable energy to inefficiencies. If we do the same for a battery electric locomotive, again, the final 3 transmission items are the same. The biggest loss is from the grid through the battery charger itself, and then a 10% round trip charging loss going in and discharge loss coming out of the battery. I end up with 36% efficiency, 64% efficiency, 36% loss. And if I look at an electric locomotive, taking power directly from the grid goes into the catenary, about a 12% loss through the catenary system itself, and then the onboard high voltage electrical devices, step-down transformer, line converter, etc., 5% loss, 95%. The same 3 transmission items, I end up with a efficiency at the rails of 77% or a loss of 23%. Now, let's, I've summarized the numbers here, and yeah, this 25 should be here and this 40 should be over here, so pardon that, I'll try to correct that for your file. But if we look at the 4 Sankey diagrams, that's how these things look. And I think this is one of the things, this kind of analysis is something that I'm finding sporadically. In fact, I did some research and I tried to do a validity check on these estimates. I've got Walter's book up there with diesel. I made my own calculations for electric, battery, and fuel cell. There's a gentleman named Christeller. He wrote an article in International Railway Journal back in March of this year. He did the same thing, a paper by Wallington and several others, which was published in Joule, a journal, and Washing and others in the same journal. And you can see, if we look at the ranges here, myself and these other 3 that I've cited here, electric locomotive, 72 to 77% efficient, going from the grid down to the rails. Battery electric, much wider, 56 to 71%. The biggest issue is, are you charging the battery electric locomotive stationary, or are you charging it in motion from the catenary, which tends to be more efficient, but you have to have more equipment. You have to have a charging system on board the locomotive to take, for example, 25,000 volt AC and put it through a charging system to charge a battery that operates in DC volts. And the hydrogen fuel cell, Range, amazingly pretty close, 17 to 25%. Diesel, I think most of the state-of-the-art Tier 2, Tier 3, Tier 4 are in 35 to 40%. But again, the three electric modes, we're looking at grid energy coming in, whereas with the diesel, we're starting out with liquid fuel in the tank. I'm not accounting for the energy that's required to get the crude, to process the crude, to ship the crude, ship the fuel oil, et cetera. So this diesel efficiency, you can't really take it. And I'm trying to figure out how to make this more equal to the grid-based energy users. Now, all this said, I want to take a very quick run here at what I call a roadmap to the future, and I'm going to preface this by saying something here. It's possible that the freight railroads and the passenger railroads might be able to keep diesel-electric locomotives and get very close to net zero by 2050 by using things such as more renewable diesel, which is the same as hydrogenated vegetable oil, or biodiesel, which has the problem with biodiesel is the more you use, the greater the NOx output. NOx is oxides of nitrogen, a precursor to smog, so it's not as good as renewable diesel. And the other thing is the renewable diesel manufacturers, how far down can they go on their carbon index? Right now, you can get renewable diesels that are down in the 50 to 60% carbon index, which is CARB, or California's method. Petroleum diesel is considered to be 100 on a carbon index. Some of the renewable diesels out there are 50 to 60. There have been some biodiesels that have been registered with California. They claim their carbon index is 10. So it's possible, you could sustain the use of diesel engines, but the problem with a diesel engine, it's an internal combustion engine. And you will still not be able to get rid of your primary criteria emittance, NOx, oxides of nitrogen, and particulate matter. You'll be able to reduce them, but you're not going to be able to get them, I think, down to zero. So that's another challenge. But moving ahead here, and I've listed, renewable diesel and so on. We just talked about that. There have been proposals to use renewable natural gas, a dual fuel engine, going back, like the experiments from, GE and EMD. In fact, Florida East Coast is running 24 GE locomotives along the east coast of Florida using LNG. And their parent, Grupo Mexico, which owns Ferromex, they have, I think, about the same number of GE locomotives also running on LNG in Mexico. But renewable diesel, where it's not new virgin dinosaur grade natural gas coming up out of the ground, it's renewable from landfills, et cetera. I don't have time to talk about it. We've talked here about battery electric and hydrogen fuel cell, which all have batteries anyway. There's been some talk about using hydrogen as an internal combustion engine fuel. I'm not going to go there. We don't have time for that. The question I've asked of people is, what's going to be your thermal efficiency? And the answer I generally get is, we'll let you know when we get there. So I don't know. Depends on how efficient it's going to be. And you're still going to get probably NOx and much less PM, but you're probably still going to get NOx. NOx is formed by high temperature combustion. And last but not least, electrification. In my view is, if you're going to do it, you have an electric locomotive with what I call a last mile battery, so that when you electrify, you string the overhead wire, you have a low overhead bridge. Classically, the approach to that, when people talk about railway electrification, we have to raise the bridge or we have to drop the track. What I'm saying is, do what they do in Europe. You put a last mile battery, you get near the bridge, you drop the pantograph, you transfer to battery power for a short distance, past the low bridge, and you go back with the pantograph up on the wire. I think there's ways to deal with this. Today's North American fleet, I'm referencing two sources of data here. The first is the North American Locomotive Review. It comes out every year from RailLink. RailLink Incorporated is a subsidiary of the AAR in Cary, North Carolina. You can go online and you can get that report every year. It's authored by Dr. David Humphreys, the data scientist at RailLink. And according to where's the, okay. Here's the pointer. Okay, according to RailLink, there are 37,600 locomotives on North America, Canada, US, and Mexico. If you go to the AAR fact book, which is published every year, it basically totals, the AAR fact book accounts for the class 1s in the US, the two big railroads that shows the locomotives they have registered for Canada, and the two big railroads in Mexico. But if you break it down between what's registered in the US, it's 28,200, which leaves roughly 9,400 for regional railroads, short lines, and private owners. If you add up these two numbers, you get to RailLink's 37,600. So, it depends. Do you want to talk about doing something in the future for all locomotives on North America, or do you want to focus on the class 1s, or do you want to focus on the short lines and regionals and private owners, or again, do you want to do everything? So you're going to see some numbers here. If you just want to look at the class 1s in the US, Canada, and Mexico, this number conveniently is 75% of that. So the numbers I'm going to show you a little later here in terms of locomotives per year, just scale it down by 25% or assume 75%, and you'll get a class 1 number only. When we talk about converting the network, this is the railroad network on North America. And The Economist magazine, over 15 years ago, from Britain, they described the US freight rail network as the envy of the world, because we basically have one interoperable, connected network that can go from the northernmost parts of Canada across the US, east, west, north, south, down into Mexico, all the way down to the Yucatan Peninsula. And you can operate most locomotives and most cars, not necessarily double stack, high clearance cars, but generally most equipment can operate from northern Canada all the way down to far southern Mexico. And it's very efficient. What I want to point out here, though, is that, again, when we look at the US network, there are 140,000 track miles. Roughly 10% of the track miles, 10% of the track miles, which is highlighted by these high density lines here, generate 30% of the gross ton miles and probably consume at least 35% of our energy. And that is, for example, the BNSF Southern Transcon from Chicago through Kansas City, across New Mexico and Arizona into LA, the UP from Chicago, the former C&W, to Omaha, and all the way out to Ogden, and then of course the traffic splits in 3 directions. You've got several high density lines in the east, and let me think here, the Southern Railway, I think the old C&O and TP from Cincinnati to Chattanooga down into Atlanta would also probably qualify for that, but I pose the question here, are we going to go from, right now we have one universal locomotive fleet. I mean, we have some low and medium horsepower, but the line haul locomotives essentially are 4,000 to 4,400 horsepower, DC or AC traction, and you can basically run them anywhere. You can fuel them anywhere, 300 gallons per minute. You can pack 192 megawatt hours of total energy into one of the fuel tanks in 17 minutes time. That's phenomenal. There's no way you can cram 192 megawatt hours into any battery in 17 minutes. It's beyond cognition here. You just can't do it. So, as we move forward here, what's going to happen? Are we going to have the same fleet burning some different fuels, or are we going to have to transition in part or in whole to some new technology? And this is where I feel there needs to be a calm analysis of all the alternatives, including electrification, for the highest density main lines. That's all I'm going to say. And that's something that needs to be done here. Last week there was a Railway Age webinar, and I was fortunate enough to be invited. I presented some of the same slides about energy efficiency, and Jason Keene, who's the vice president of Oliver Wyman Rail practice at Oliver Wyman Consulting, he made a presentation, and I've copied one of his slides here. I've actually copied 2 slides, and he pointed out, as I've done in previous presentations, that heavy-duty trucks right now, the 8 largest fleet operators, J.B. Hunt, Swift, Schneider with the orange trucks from Green Bay, Werner from Werner Transportation from Omaha, the 8 or 9 largest fleet operators, they wholesale off their entire tractor fleet roughly every 2 years. And they buy a whole new fleet. And they do that for 2 reasons. One, they avoid engine and transmission overhauls, and the trucks get cascaded down to the used market. It goes down to, the large regional truckers, and then eventually, after about 7 years, it maybe goes down to the mom and pop fleets, the owner-operators, etc. But what he shows here graphically is that between over a 30-year span, the trucking industry can have 10 to 15 turnovers of technology. If you replace your tractors every 2 years, in 30 years, you will have been able to acquire 15 turnovers of technology. We, on the other hand, excuse me, have essentially a 30-year locomotive, and we replace the engine, and that's all I'm going to say here. So there's this difference here between heavy-duty trucking and technological turnover and the railroad industry. One other thing that Jason proposed, and I've copied his slide up here, is that in his opinion, I'm going to read the top, it says, "Moonshot for rail, we put boots on the moon in 8 years." And what he's proposing is a moonshot. And by the way, in this University of Cambridge report on the aviation industry that just came out in the UK, they also talk about a moonshot. And their idea of a moonshot is using liquefied hydrogen fuel for airliners. But as I've shown here, I agree in part with Jason, but there's a difference in opinion here, some of the details. In my opinion, what I call balkanized experimentation and onesie-twosie tests of new types of locomotives is largely unproductive. It's proving that we can build a locomotive, we can test it, it moves, it makes some noise, it may generate no emissions, etc., other than water and some heat, but it doesn't really prove that it is commercially sustainable. And I feel that we need to have focus, we need to have an industry consensus, and we need to have an honest, unbiased economic analysis of many of these proposals, and a schedule ultimately, and I'm going to talk about that. If we have to go to new technology, how much time do we have? How much effort are we going to have to expend? And can we do this by 2050? And the key word here is bankable assets, and I'll talk about and explain what that is. Now, I mentioned I want to take a little cakewalk here. Werner von Braun, I'm sure you've all heard. He was the German scientist who became the head of the rocket program and was largely responsible for putting US astronauts on the moon. And the original plan by NASA, starting in, they talked about it in 1958, and then when President Kennedy made his announcement, I think at the Air Force Academy in Colorado in 1960, that we are going to commit ourselves to putting men on the moon and to bring them home safely by the end of the decade. NASA was put on a treadmill here, a 9-year treadmill, to do that, and they accomplished it. And basically, the thinking at NASA was originally one big massive rocket. It was called the Nova, and it would be direct to the moon. It would land on the moon, the astronauts would go and do their thing, collect their rocks, take photographs, etc., get back on the rocket, and it would come back. And it was a massive rocket. The counter proposal, which Warner von Braun did not necessarily agree with, he did not agree with initially, but he came to change his thinking, was what turned out to be the Mercury program, launching one astronaut, not orbital, but short movements into space, graduating to the Gemini project, 2 astronauts and making orbits around the world. Then the first Apollo mission, which was to fly to and around the moon. And the first mission was Christmas Eve of 1968. I remember that. I was a freshman in engineering school. And I was with my parents at a aunt and uncle's house, watching it on a color TV circa 1968. And I still remember that. I still remember that. Men going around the moon, and then the blackout, and then coming out and talking about the good ship Earth. But that was followed ultimately by orbital trips around the moon, and finally the lunar lander and coming back up to the mother craft. So it was a 5-step process. And it was all accomplished largely with the Saturn rocket, and it was done in sequence, in stages. But if you go back and look at this project in terms of what was done, starting with the Atlas rocket for Mercury, and then the early Gemini, and then the first Saturn rocket, and then the Saturn 1B. This one became the second stage, et cetera, working up to the Saturn V rocket compared to the Nova. You can see the difference here. The Saturn rocket that put men on the moon was 33 feet in diameter. It weighed just under 3,300 tons at launch. The Nova that had been suggested was twice as heavy, 50 feet in diameter, 17 engines instead of 11. I mean, it was just, von Braun was right. This is not the way to go to the moon. And rockets never blow up, that's right. Bigger ones blow up. When they blow up really well. But anyway, this leads into what I'm going to talk about here, a program focus. In my opinion, if we're going to do a focused program, instead of a moonshot, it needs to be what, again, I call a moon program. It needs to be in controlled, managed steps. And the first step, in my opinion, as an engineer who's been involved with locomotive design, maintenance, operations, failures, and sometimes even early scrappage, start small. I want to start with switchers with low horsepower because they are tethered. They don't go out, over 1,000, 2,000 miles. You can train people. You want to start with a switcher. And if you can't maintain a switcher, for whatever reason, don't think about line haul. And the second step is to then go with the line haul fleet. But again, this is where I think we tend to fall into the moon trap. A lot of people, a lot of industries fall into the moonshot trap, is what I call it. Now, has anybody heard about reliability growth testing, RGT? Okay. RGT was originated in Erie, Pennsylvania by an engineer, J.T. Duane, and you can find Duane charts and so on. Basically, his discovery, and he worked on motors for the U.S. military. His discovery was that you have to establish a reliability goal for a machine, and you have to measure pre-production machines, pre-production, not experimentals. You want pre-production because you want them made on the actual line by the people making the actual parts, not engineers. And you measure reliability, and when parts fail, if you've not gotten to your reliability goal, you take the failed parts out, you analyze why they failed, you redesign them, you put them back in. It's a make, break, fix, and retest process. And when you get to your reliability goal, you've achieved success. And this was first applied to the Huey helicopter in Vietnam, or Black Hawk helicopter. When the Black Hawks first went into Vietnam, they had to have a power plant mechanic work on the engine after 1 hour of flight. And by going through an RGT process, I think in a year's time, they were able to get flight time up to 4.4 hours before the turbine engines and the transmissions had to be worked on by a power plant mechanic. But what I have seen over and over and over in our industry is that we start out with some test locomotives, we do some early validation, and we don't put them out and let railroad people get their hands on it at 2 a.m. on a rainy Sunday night. We love to test things at the test tracks at Pueblo. And if you ever go out there, the people who are doing all the tinkering on those locomotives are from the builder. They're engineers. And that's not real railroad. And what I have seen is, by doing that without doing RGT testing, real valid shakedown, you run the risk that the locomotives that go into commercial production will fail or they will not meet your reliability goals. So again, this is how I like to see new locomotives introduced. And this period here of RGT, make, break, refine, and retest. One builder did this in the 2000s when they introduced a new tier level of locomotives. They built 50 pre-production locomotives, gave them to 3 railroads, and they were operated for just under 2 years. They accumulated 42 unit years of experience in about 19 months of time. They failed parts, they fixed the parts. It should have been a great introduction when it went into production. When they went into production, shortly before that, they changed a couple of key parts, guess where? In the diesel engine. And the first production units came out and they failed miserably. It was recoverable, but it's a lesson that you have to have some patience. Now, the builder funded the locomotives. They were ultimately rehabilitated and sold to the railroads, so the builder recouped its money. But the problem is they had this money tied up in 50 pre-production locomotives for 2 years' time. So again, to me, the best approach is reliability RGT testing. I have XX. It could be anywhere from 25 to 50 unit years of experience. I can test one locomotive for 50 years, but I'm going to lose because I can't wait 50 years to introduce a new product. Or I could test 50 locomotives for 1 year, but I'm not going to see a dropout of components in probably 1 year's time. So it's a balance between the art of testing and the science of RGT. You have to come to a reasonable compromise. There's a chart. It's called TRL, Technology Readiness Level. It was produced by NASA, largely to sell the space shuttle to Congress. And the space shuttle was ranked at TRL 9, which means ready for launch. Unfortunately, there were five space shuttles built. There were 135 launches. 2 of them were catastrophic with loss of craft and loss of crew, the Challenger and the Columbia. And that's not real world for commercial aviation, obviously. So the TRL scale is good for experimentation. And I've put on here, for example, where I think fuel cell locomotives are today. Battery locomotives with stationary charge. There's some work going on about battery locomotives with mobile charging. I've heard some rumors. But diesel electric locomotives are up here on this blue chart, which is, I found from Australia. They call it the commercial readiness level. And at the very top, level 6, what do we see here? Bankable asset class. That means if I want to buy these, if it's at commercial readiness level 6, I should be able to go to an insurance company, a bank, whoever who's got money, and get money to buy these and lease them and give them a good economic return and not run the risk that these locomotives are going to get scrapped after about 7 years, which I did once with some 6,000 horsepower locomotives. So the key thing here, I have seen 2 generations of two brands of 6,000 horsepower. The Green Goat battery hybrid, diesel battery hybrids, and the genset locomotives, they were all basically rushed into operation and commercialization without going through adequate RGT. Okay, fleet conversion numbers. Again, 160,000 track miles, 206,000 on the whole continent, 6 railroads in the US, 2 of which are in Canada, 2 of them also operate in Mexico, plus regionals and short lines. Dieselization, it took 40 years, 20 years of development from 1920 to 1940, and then commercialization, round number 1, to get rid of steam locomotives was 1940 to 1960. How much time would it take? Remember the railing number, 37,000. That's what where I'm going with this. How much time is required if we have to convert every locomotive on North America? And you can scale this down. And I'm breaking it down into doing basic research and development, engineering, reliability testing of pre-production locomotives, and finally, going into commercialization. And again, if you want to break this down, if you want to look at just the 23,600 locomotives on the Class 1 railroads in US, Canada, and Mexico, just the Class 1 or Class 1-like railroads, the big units, you can scale that down by 75% from 37,000. Okay, I'm going to start with the year 2025. I want to end at 2050. If I assume that I can do 1 year of engineering combined with reliability growth testing, which is way too short, I'm going to start, I'm going to have to modify over 25 years, 1,500 units per year. You can see as I spend more time doing engineering and testing, I have less time for production. So the conversion number goes up. Again, if I do 5 years of engineering, R&D, reliability testing, I end up with 21 years to do the conversion. If I spend 7 years, I got to cram all my achievements into 19 years. And a point of reference here, the best year that the railroad industry in multiple decades was able to achieve was right around 1,550 new locomotives in the year, I think it was, what year was that? 1999 or 2000. So again, you know, assuming we're going to modify or make new locomotives, these are the number of units you have to accomplish in the ever decreasing number of years you have to get to 2050. Now, how quickly can green hydrogen replace diesel? And this is where we talk about fuel cell locomotives. Right now, there's roughly 60 billion US gallons of diesel fuel used in the US. 40 billion goes to heavy-duty, mostly heavy-duty trucks. Ag and construction consumes 14 billion. Rail is about 3.9 when you add up freight and all the commuter and passenger and Amtrak. And waterway, I think, is about 2.4 billion. I've rounded them up here, rounded them up or down, 60 billion gallons. Have you all heard about hydrogen hubs from Department of Energy? Okay, anybody not heard? Okay, you can look it up. The Department of Energy has, they are making the final selection of 7 proposals around the country, obviously because it's a political decision, where prototype hydrogen production plants will be built. DOE is contributing $7 billion, and the private partners are to contribute $40 billion, for a total of $47 billion on these 7 hydrogen hubs. And the goal is to produce just under 3 million metric tons, which is, just under 3 million metric tons per year by 2030. That's equivalent to just under 3 billion kilograms of hydrogen, and a kilogram of hydrogen is roughly the energy equivalent of a gallon of diesel. Fortunately, not easy conversion. So in order to replace, rough order of magnitude, 60 billion gallons of diesel, you would need 20 times this project. 20 times 3 billion would give you 60 billion. 20 times $47 billion is $970 billion, just under $1 trillion. So let's add, we're going to go shopping to Costco. I want enough hydrogen plants using, I'm going to use the math here from the hydrogen hubs as an example. I want to buy enough hydrogen plants to produce 60 billion kilograms of hydrogen in a year. And oh, by the way, I need somebody to help me get $1 trillion green grid out the door as well, because in order to make green hydrogen, I have to have green electricity going in, and that means a generation system and a grid that is based solely on renewable energy. Can't have any thermal. I can have hydro, but it's limited. I can have some nuclear, but you know, we're not going to get into the debate about nuclear and nuclear waste and so on. I can't have thermal generation. I can't have natural gas turbines. I definitely can't have coal. So $1 trillion here and $1 trillion there. You know, you better have an executive membership at Costco to get your, what is it? I think I get 5% back every year. You know, anyway, $1 trillion here, $1 trillion there, so I get half $1 trillion back, or I get $1 trillion back. No, I get $50 million back, whatever. Big money. So is there enough hydrogen by 2035 or 2040? I think we're not going to have sufficient zero carbon hydrogen quickly. It's going to take time. So this is another factor that's going to enter into any decision to use hydrogen fuel cell locomotives. I did a calculation last year at the environmental conference, and you'll see this later, but the biggest plant in China right now, it's 30 million kilograms per year, 848 million US dollars, so I'm pricing it up with labor and material costs, just over 1 billion. And the way I look at it, you know, to put one of these plants at Belen, New Mexico on the BNSF Southern Transcon, by my math, you got enough money to string catenary on 2,400, one of the two tracks between Chicago and LA. But it's an order of magnitude calculation. I'm not trying to do battle with any entities here. Last thing, suggested path to future locomotives. In my opinion, people have said, well, you know, there's these great electric locomotives in Europe, in Sweden, in Germany, and so on. I don't want to take European locomotives and Americanize them. They're not designed for operation on North America, and basically the approach, again, you know, there's great differences in the trucks and the traction motors, the car body. You don't have switching steps. You don't have the million-pound underframe. There's a lot of work to make this locomotive or others like it pass the FRA and AAR regulatory and standard requirements. So what I'm saying is, forget about Americanization of foreign locomotives. Fortunately, with the locomotives we have, I think one of the pathways is to take existing locomotives. You basically got the engine, the alternator, the cooling system, etc. And if you look at the battery electric that was made by Wabtec in Erie for Roy Hill, it's a 7 megawatt hour. It's essentially an Evo 4,400 horsepower Evolution AC locomotive that basically they started from scratch, but I think basically it's a highly modified diesel electric locomotive underframe, same trucks, same traction motors, etc. What I feel that basically we've already got a platform that, you know, you can have diesel electric locomotives, you can turn them, or you could make new similar battery electric or fuel cell electric or even straight electric locomotive. So I think, you know, the talk about we need 7 to 9 years to engineer a new electric locomotive, I don't see that as realistic. I think that's excessive. Best approach, again, I feel convert existing locomotives. The 4-motor, another thought I have is if you put AC motors under, let's say, a modified GP38 4-motor, a 4-motor locomotive with AC traction motors should be able to pull as well at low speed as a DC locomotive with 6 motors. You can get more adhesion, more work down to the rail with AC motors. So, you know, there's a couple of things that need to be thought about here if we're going to pursue this. And from our history here, back in 1990 to 1992, the AAR had a working group. I think I'm the only person still in the industry who was a member. There were 26 railroads, including Amtrak and the former British Columbia Rail. And the mission was, the the mission was to develop a specification for 26 test locomotives using AC traction that would be distributed to the member roads. The railroads would pay for this through the AAR. And the AAR economics staff in Washington was also tasked with looking at the economics. And the first pass, they came back and they said, we can't afford these AC locomotives. The premise was that AC traction motors would eliminate the extensive and expensive maintenance of DC traction motors, which have commutators, carbon brushes, etc. And the ROI analysis proved that was bad. You couldn't afford the locomotive. There was one railroad that said, wait a minute, how much more tonnage can I haul with AC motors and the same horsepower? And when that calculation was run, it became out positive. Unfortunately, or fortunately, the Burlington Northern and Electromotive Division of General Motors, in 1992, BN signed a contract for 400 SD70 Max, and that launched AC traction. The idea of a test fleet supported by the AAR and all the member railroads died, and I was out at Pueblo last week, and the 4 SD60 Mac prototypes have now been donated to the FRA, I think ultimately to be crash test units. And I was on one of them and I found a wiring diagram, and the EMD order number started with the numbers 89, which tells me that EMD actually started working on this technology back in 1989, and it wasn't announced with a contract until 1992. But anyway, that brings me to the end here, and I hope this was informative. Again, I am not saying that electrification is the way to go. I'm not saying that hydrogen is not the way to go. There are a lot of details to examine and a lot of decisions to be made, but the key thing is time is passing. Thank you, and turn it back over to Dr. Barkin. Thank you.
So do we have any questions?
Hello there. My question was on, you had that diagram of commercialization and, readiness. You ranked, was it like European electric and electric with battery for last mile as very high compared to the American? And I was just wondering, is that due to the lack of electrification of the rails in the United States? Or is that due to like differences in like locomotives, essentially?
I think that the real answer to your question, which is a very good question, and just forget the slide that I'm fumbling around trying to find the right slide, doesn't matter. The largest freight trains in Europe are roughly 1,700 tons and about a half mile long. And it's because most of Europe uses the what do they call them, the jack, screw, and hook couplings. They don't use the Janney type coupler that we use here, which is good for, on a good day, 375,000 pounds of pull. So to try to run a train like we run it here with often with head-end power, with the tonnages we haul, you would not be able to operate a train that big in Europe. In fact, a couple of years ago, there was a big to-do in Europe. They're now running a train that is twice as long as always, because they put 2 trains together and they put 1 locomotive on the front and 1 at the rear, basically distributed power. Guess what? We've been doing that for 25 years. Okay, so the biggest difference, freight trains in Europe, and I include the UK in this, they basically are operated at a power level that keeps them out of the way of passenger. In fact, I was at a heavy haul conference in Dallas, I think in 2004, and there was a gentleman from DB, Deutsche Bahn, and he was talking about the challenges of moving iron ore trains in the Ruhr Valley and keeping them out of the way of passenger trains. And as I recall, they were running 1,700 foot long iron ore trains, which is we'd never make money here. But they were operating these trains with sufficient power to get them up to 60 miles an hour. There's no way in our economy that you can run an iron ore train at 60 miles an hour and make a profit. But they were doing that to stay out of the way of passenger. So again, the emphasis in Europe is on speed and not on lugging capability. Does that answer your question? Okay. Any others? Yes.
So I guess this is more so just curiosity. When you mentioned the electrification and then like the last mile battery, has there been any talk of like maybe doing, I guess the opposite, where it's the battery does the most of it, but well, I guess this is kind of based off like the charging battery, the moving charging battery, just to a larger extent. Has there ever been any talk of like doing that for steep grades or like parts where the diesel engine isn't as efficient?
Good question. In fact, the study that we're wrapping up now for the FRA, the report isn't going to be available for probably, I don't know, 6 months. It has to go through the FRA vetting before it actually is released, but I can say a little bit about it. One thing we've looked at is just in the limited time we had last week, part of the project was creating a spreadsheet that is a financial model where you can put different inputs in, different assumptions, and you can calculate returns on investment. And one thing we looked at was we call it a taconite loop in the U.S., moving taconite ore trains to a dock. And we looked at putting overhead catenary and running electric locomotives, and the ROI was absolutely horrible. We also looked at battery locomotives with stationary charging, and we looked at battery locomotives with some intermittent catenary where you can recharge, and that positively changed, I think it positively changed the return on investment. So what happens is when you have a battery locomotive and you use discontinuous catenary, instead of having catenary from A all the way to J, I have catenary from A to B, from E to G, from K to S, for example. And I run on battery power in the gaps in between, and when I hit the catenary section, I raise the pantograph and I charge the batteries. The alternative is have a battery locomotive that can go from A, what did I say, to S or T, whatever, all on battery charge without running out of, depleting all its charge. And this is where you get you start to get economic trade-offs. How much catenary I'm putting in, what's the capex, what's the cost of maintaining it, versus can I make the battery locomotive smaller, put fewer batteries in because batteries wear out, they have to be replaced like a diesel engine, etc. So you have these different cost curves. But that's one of the things with battery electric locomotives. The other thing I'll mention, the downside of a battery locomotive, if you do just stationary charging. Let's assume that to go from this origin down to that terminal on the other end, let's assume that it takes, I'm just going to throw a number out there, 10 megawatt hours of energy to move the train from here to there. With an electric locomotive, I will use the same, if it has the same power rating, tractive effort, unit time, etc. at the rails, I will use the same 10 megawatt hours from the grid, but those 10 megawatt hours will be drawn down from the grid from this point at this moment in time all the way across, and let's say it's 10 distances, so I've got 10 megawatt hours total, 1 megawatt hour per unit time, per unit distance, whereas if I have a 10 megawatt hour battery locomotive, I want to slam all 10 megawatt hours in that battery as quick as possible so I can get that locomotive back out to run productively. But now I'm ringing the doorbell of the utility and I'm saying, I don't need 1 megawatt per hour all the way for 10 hours. I need 10 megawatts and I need it now. And that's where you get into demand charges from the utility. You see, I mean, it's like filling a bucket. It's like running with a long fire hose. Whereas you want to, you got a bucket and you want to fill it with a fire hose and carry the bucket across as it leaks. That's the difference between electric and battery. Yes, sir.
Has there been any look into like swappable fuels? Like you slide out a tank and you slide something else in, or you switch out a battery or something that's already full?
Can you have a,
the
for
question-
example, a replaceable battery pack?
I'm repeating the question
And-
with the microphone I suggested. Has there been any look into something that can be swappable, like you take out a fuel tank or a battery and you slide a new one in that's full?
Yeah, there's a container terminal, trying to think of what it is, Long Beach, LBCT, you can look it up. Long Beach Container Terminal in the Port of Long Beach, which is, next to the Port of Los Angeles. LBCT is a highly automated container terminal. I think they have about less than 30 people running the whole terminal. And the shuttle trucks that take containers from the dock alongside a ship to the stacking racks, or from the stacking racks back to the dock where they're picked up and put on the ship, those shuttle wagons are battery powered, and they have basically they have a replaceable battery. And when the battery gets down near minimum, the shuttle basically tells the computer that controls everything, my battery is about to die, and it goes to an automated building where they have a robot that actually picks this, 20-ton battery up and takes it, puts it on a charger, puts a fresh battery on, and this automated shuttle wagon goes back out and goes back to work again. So that has been done. But when you start talking about the range of capacity we're talking some pretty big batteries here. And now obviously you're dealing with what kind of machinery are you going to have, and where do you put it in the yard? If it's a train that comes in and you want to do it while the train is like here at Champaign, where do you want to put this machine to change the batteries, knowing that you may have locomotives on the front of the train and 1 or 2 locomotives in the middle or at the rear of the train? Do you stop the train multiple times at one robot, or do you have them spaced out? It gets pretty complex. The answer is yes, but. Does that answer it for you?
Yeah, thanks.
Anything else? Yes, sir.
Yeah, right there.
You have a radio announcer voice. Go ahead.
Thank you. So what was my question? I guess this is probably in like the research, and it's probably still being researched, but specifically for the large batteries, I was kind of curious about like fire safety and like new technologies there, because like electric car battery fires are bad, and this is so much larger. Like,
Yeah.
is there a lot of research going into like making that safer or trying to change that?
I don't know what research has been done, particularly on the locomotive size. I know there is a lot of research going on regarding batteries in general. Back in, I think it was August, there was a Tesla Class 8 semi-trailer, a Tesla battery tractor on Donner Pass. The driver allowed the truck to go off the road, ran into a tree, he survived, and it took the local fire department and the forestry service, I read in the paper, it took 50,000 gallons of water on Donner Pass on I-80 to extinguish the fire, and they shut down I-80 for about 15 hours. So I mean that was like just under 1 megawatt hour of battery capacity. So yeah, it's something, and then again, hydrogen has flammability issues as well. It's exceptionally flammable.
And our trains never derail.
Well, that's why we count on you to come up with the statistics. Yes, sir. Oh, I'm sorry.
In your first 2 slides, you had an example where hydrogen was the combustion, but in the actual efficiency diagram, you had a solid state fuel cell. So
Right.
in locomotives, which generally is more favored?
Well, okay, if you're going to use green hydrogen with a fuel cell, the hydrogen is technically not a fuel, it is an energy carrier. Because when you make hydrogen in electrolysis, you're creating hydrogen molecules, 2 hydrogen atoms combined. When you put it in the fuel cell, you're splitting the hydrogen molecule, and when you do that, you combine hydrogen and oxygen to make water, and you generate electricity. So in a fuel cell application, hydrogen is an energy carrier. You can also use hydrogen in gaseous form as a fuel by injecting it into a diesel engine.
So I guess
So that's the difference. One application, hydrogen is a fuel, because you're burning it, and in the other application, you're actually carrying electrons into a fuel cell.
That makes sense, but my question was more, is one more favored over the other? Or is one more efficient?
Well, I think in general, people would like to see, I'd like to use hydrogen in diesel engines because I can keep the diesel engine. So I've got an installed base of diesel engines, but I mean, the question is,
So it's like a go.
can you modify all the diesel engines, or are we talking just about the latest generation of, because there are different generations of diesel engines out there. So they're not necessarily all modifiable. We learned that with natural gas. Did that answer the question?
Yes.
Okay, thank you.
So I want to give at least some of the online people a chance, and members of the class, of course, are going to have a chance to talk to you later. So I'll take a few of the online questions. We'll get, we can't go through all of them. There's a lot. So for the benefit of the online audience, we'll provide all of these questions to Mike, and he can potentially answer them. But here's one. It seems like Class 1 railroads are on the fence about adopting new locomotive technologies in the first place. If and when we get past that, do you have any insights into who should fund capital-intensive new technology?
Wow. The biggest question first. Well, I think the reason, the phrase, the railroads are on the fence, is this is going to be, if you're going to have to go this route with brand new propulsion technology, it's going to be like steam to diesel. It's going to be a major undertaking. And it's not going to be cheap, and there will be risks. There will also be opportunities, but it's going to be a big challenge. So I think there's a right now there isn't enough evidence which way to go, and not enough evidence also, in my opinion, means there isn't enough economic evidence of which paths are most likely to lead where you need to go if you're going to have to do that.
Well, this relates to your slide about Supertruck and the fact that DOE invested significant R&D funding in that. And do you foresee that happening on the railroad side?
I think personally, I think it would be good. I want to mention here that the Supertruck is resident in the Department of Energy in a program called Supertruck, and the head of the program is Dr. Sadiq Khan, and I recently became aware of the fact that his title was manager of Supertruck, and his new title is manager of Supertruck and Rail Decarbonization. So does that mean DOE is interested, or does that mean he's got two more words on, or three more words on the end of his title? I don't know.
Okay. Well, here's another question. Have you tried penciling the effect of energy recapture on the efficiency of various electric technologies? In other words, regenerative braking and the...
Yeah, there will be some advantage to capturing regenerative brake. Right now dynamic braking, you put it into the resistor grids and you dump the energy to the atmosphere as heat. Regenerative braking is where you take, instead of boiling it off as heat, you put it back into the catenary, you put it into the batteries, and there's a lot of hope for this with battery locomotives and fuel cell locomotives. The problem is, depending on the route in the train, if you're generating a lot of dynamic brake, eventually you'll get to the point where the battery is charged, and the battery will cry uncle, and you're not going to be able to put any more into the battery. You'll have to revert back to dynamic brake and wasting it to the atmosphere. So it's not an easy one-size-fits-all solution. There's some potential, but I think to some extent it's been over considered and over-promised. It's going to be very route and train dependent.
Okay. Well, I am going to suggest, even though there are more questions, that we wrap it up.
Okay.
Now, coming up on 2 o'clock. Again, I want to thank you for an outstanding and very timely presentation, Mike.
Thank you. Thank you very much.